Okay, guys. All right, so the goal of this problem was to take wet air at a hot temperature and turn it to dry air at a temperature around room temperature. So again, whenever we get a phase diagram, let's label our regions. Solid at low temperatures, liquid at higher temperatures, and vapor at the highest temperatures. All right, and then these lines are going to be our two-phase regions that are just bounding the single-phase regions here. For the solid vapor and liquid vapor lines, points on here are corresponding to 100% humidity. That's where the vapor is completely saturated with water. Okay, so now we're going to find our 2 points that we're trying to go between. At 29 degrees, we have a vapor pressure, partial pressure of H2O, 0.04 atmospheres. So that's 100% humidity. So if we're at 75% humidity, we're going to be at a partial pressure that's 3/4 of that. So 0.03 atmospheres. We can do the same thing for 18 degrees C. It's just going to be 10% of whatever the vapor pressure is at 18 degrees C. Okay, so we're going to have to remove some of the water from the air. And the only way we're going to be able to do that is by condensing it. So let's start by trying to pressurize our air and seeing if we can get enough water out. We're trying to end up at 1 atmosphere with a partial pressure of 0.002. So that means we want a mole fraction of water of 0.002. Right? Well, our pressure here at this point is going to be 0.004. And the more we pressurize it, that's going to stay the same because that's the equilibrium value for the partial pressure of water. So in order to condense enough of it to get the mole fraction to 0.002, we're going to need to pressurize our air to 20 atmospheres, which is really, really high and above the specification of the problem. So this way of just directly pressurizing everything to condense enough water vapor is not going to work. Okay? So if we can't move upwards to the line, let's try moving sideways, cooling it at constant temperature. This makes sense because we know we want to end up at a colder temperature anyway. So we're going to have a cooler. So why not just use that cooler to condense the vapor? As soon as we hit this point right here, we're going to start condensing, which is going to lower the partial pressure of water. So as we keep cooling, the partial pressure is going to drop and drop and drop, which is why we're going to be coming down following the equilibrium. All right, so we want to end up at a partial pressure of 0.002, so we can just follow this line all the way down here, and then just heat it up to where we want. All right, so all we need is one cooler to cool it down to the temperature we need, which would be at around -12, -13. And then a solid gas separator to remove the liquid and the vapor, because we only want the vapor here. And then finally, a heater to heat it up to the temperature we want. Okay? That's part A. All right, part B, now we're considering we can't go into these regions here. So in our first one, we had cooled it down all the way to here, and then used a solid gas separator to take it out. So now we're saying, all right, how do we do this without using a solid gas separator? So we can't ever cross this point. Again, we know we need to have 0.002 mole fraction in the final the final product, and we saw that if we're pressurizing it here, we'd have to go to a pressure too high to be able to do it. But what if we only went part of the way? If we instead of going all the way to 20, just went to 4 atmospheres. Let me go back here. So we see that this is going to give a partial pressure of 0.008. So if we once we go up here and follow this down, we can hit the point 0.008. If we were still dealing at only 1 atmosphere and we needed to get a partial pressure of 0.002 by heating it up, and going down here, we would get into this region that we're not allowed to, right? So by pre-pressurizing our vapor, we can reach our 0.002 mole percent by going to the higher partial pressure of 0.00 atmospheres. So as following the process, we're going to pressurize it from 0.03. We're going to hit the equilibrium region. We're going to continue to pressurize the total mixed vapor mixture, but the partial pressure of water is going to stay the same, because as we increase the pressure past 1 atmosphere, the water is going to condense. So this is going to keep the same pressure here. The total pressure is going to increase. Now we can cool it down to get our partial pressure that we want. And then by expanding down to 1 atmosphere, we've now lowered the partial pressure to be exactly what we want. And then we just heat it up to where we were. All right. So the idea of all of that is we want to get the correct mole fraction of water in the final product. So this is drier air. There's an actual physical lower amount of water molecules in the vapor. And it's easier to do that if we first pressurize the total vapor mixture, because then we only have to cool it down. We have to cool it down less to reach the same mole fraction that we want. So in the final flow diagram will look like this. We pressurize it here. Notice that the partial pressure of water is still going to be the vapor pressure. It's never going to go higher than that, while the total pressure is going to increase to however much we want. And here we're specifying 4 atm, because this is the mole fraction that we want. Then we cool it down to the temperature we want, separate the vapor and liquid, expand it to get down to 1 atmosphere, because we want the total pressure to be 1 atmosphere, and then heat it up to the temperature we want. Any questions? All right, we can start on the design one now.